Okay, so somebody asked number 4. They got a different answer than I did. Okay, so in order to find two unit vectors perpendicular to those two things, there's sort of 2 steps to that problem. You first have to just find 2 vectors that are perpendicular to those two. And what operation are you going to use for that? Cross product, yep. And then, so the cross product will give you one vector that's perpendicular. How do you find another vector that's perpendicular?
You switch the order.
Yeah, just switch the signs of all of those. Okay, so if you have 2 vectors, say, so these are the 2 vectors, but I'll hold them a little crooked. So if you take the cross product of this one with this one, because of the right-hand rule, it'll give you a vector that's perpendicular to both of them going that way, okay? There's another vector that's perpendicular to both of those, and it's in the exact opposite direction. And the way you get that is once you have the components of this vector, just multiply it by -1, and it gives you the exact opposite. So, so the first thing is take the cross product, and it doesn't matter what order. So I'll take the cross product of 1, 2, 3. And 5, 2, 1. Okay, so let me do this on here. So this is vectors number 4. Okay, so what I'm doing is I'm taking the cross product of the vector 1, 2, 3 and the vector 5, 2, 1. And that gives the vector -4, 14, -8. Okay? So that's one vector that's perpendicular to both of those two. If I had done the cross product of 5, 2, 1 cross 1, 2, 3, I would have gotten the opposite signs on everything, you know. But in the end, we'd get the same pair of vectors. But now the question asks for a unit vector in that direction. So what's a unit vector? Well, first, so I'm using a TI-89 right here. And so I'm using the function cross P. I'm writing these vectors as 1, 2, 3, comma 5, 2, 1. Those need to be semicolons and not commas because these are column vectors, column matrices.
Does it matter in this case?
Like if you used commas?
I guess it still works.
Okay, still works. I guess maybe I've never tried that, but it will matter when you start multiplying by matrices. So I would get in the habit of doing this for vectors. And then take the unit vector. So now there's another function that a lot of these calculators have. If your calculator doesn't have it, then you might want to just enter this this program in your calculator, and I can help you do that. But so let's say that this vector u is -4, 14, -8. Now we want the unit vector in that direction. So I'll give it that, the fancy hat says that it has a length of 1. And what this function I use does is just divide by the magnitude of that vector, so you get negative 0.241, positive 0.843, negative 0.482. So that's one vector perpendicular to both of those. And I did this with the function unit v of the answer I got in the first step. And then the other answer, so let's call that. So if this is u1, this is the unit vector in the direction of u1. Then the other unit vector perpendicular, just switch all the signs. So 0.241, negative 0.843, positive 0.482. Any questions about that? Yep.
Right, left our answers as like exact. So
Oh, yeah. Sure. I'm trying to think if that, yeah, there's no problem with that.
Sure.
I'm used to just doing everything as decimals because I'm used to doing all this in computer programs, and so that's how everything propagates through computer programs. But any other vectors questions? Okay. So I'm going to keep giving you those vectors questions, but I'm also going to start going through some mathematical stuff we're going to need for this class. Okay, so I want to talk about derivatives of vectors. And I want to make a distinction that should terrify you to your very core. Derivatives of vectors in non-rotating coordinate systems. This is going to be the first class where we're going to later on do calculations where the coordinate systems are rotating, okay? And it's going to bring up a bunch of complications. But for now, we're just thinking of these vectors being represented by, so what does it take for a coordinate system to be able to be used for Newton's laws? An inertial coordinate system. Do you remember that from Physics 1? There are two requirements. Like, you can't, like, if you slap a coordinate system on the side of a bus, you know, and do all your measurements based on that coordinate system, there are going to be a lot of cases where it looks like Newton's laws are violated.
Is this where the inertial observer comes in?
Yeah. Mm-hmm. And so what an inertial coordinate system requires is a non-rotating coordinate system and a non-accelerating origin, okay? So, like if you tried to do, like for example, imagine that you drop an object just in free fall, okay? And you measure this object with using a coordinate system that you also drop. You know, you put a coordinate, you can think of a coordinate system as like a video camera, you know? So imagine that you drop this video camera. Actually, you've maybe seen people do this with GoPros and stuff, people, you know. So what do the measurements look like as these things are accelerating down? Well, you know that gravity is making this thing accelerate down at 9.81 meters per second squared. But what does the falling camera think it's doing? It just sees this thing the whole way down. So it thinks it has no motion at all, you know? So now put that in Newton's second law. You have a weight force acting on this object, but this accelerating video camera says that this thing is at rest. And so F equals ma appears to be violated, okay? And so, yeah, if you want your calculations to work with Newton's laws, which we do very much because it's a very useful tool, your coordinate system has to be non-accelerating and non-rotating, okay? Well, unfortunately, sometimes you can't control where your camera sits, you know? Like, if you're trying to do calculations of things using a camera that's on a satellite, you know, you don't always know what the orientation of this satellite's going to be. It could be rotating. It's definitely accelerating because it's in orbit, you know, so it's not moving in a straight line. So you have to correct for the fact that this is a non-inertial coordinate system, okay? And so we're going to get into that later, and I think it's one of the most interesting areas in this class. But that's why I'm making this distinction now. So first of all, we're just going to deal with the coordinate systems we're used to. They're fixed on stuff that's not rotating, not accelerating. What about fixing your coordinate system on the surface of the Earth? You know, the Earth is rotating. Does that cause a problem? Taking measurements using a video camera that's rotating as the Earth rotates? Yeah, it does. But fortunately, it doesn't make much of a difference because the orientation of a coordinate system fixed to the Earth is changing very slowly, you know? Think about it as an angular velocity. What's the angular velocity of the Earth? You know, if you think of angular velocities in an angular velocity would be like 4 radians per second. How many radians per second is an object rotating that's fixed to the Earth? It's 2 pi radians over 24 hours. So 2 pi divided by, in parentheses, 24 times 60 times 60. It's a tiny, tiny angular velocity. And so only if you're doing the most precise calculations would you ever notice the fact that the Earth is rotating. What do you get? Did you do it?
Yeah, 7 times 10 to the minus 5th.
Yeah, right. 7 times 10 to the minus 5th radians per second. So yes, it does affect things, but not very much. Okay, the second thing we're going to talk about is product rule for vectors. The third thing we're going to talk about is the chain rule for vectors. And the last thing we're going to talk about is solving ordinary differential equations using the method of separation of variables. Okay, so I'm going to start with derivatives of vectors in non-rotating coordinate systems. And so if you have a vector, let's say this vector u is equal to ux as a function of some variable, let's call the variable x, you know. Uy, that's a function of x, we're just dealing with a single independent variable. Then the derivative of this vector with respect to x is just equal to, for the first component, dx, dux, dx. For the second, duy dx. And for the third, duz dx. So as long as the coordinate system is not rotating, in this case, it could even be accelerating. It doesn't have to be an inertial coordinate system. The origin could be accelerating, but as long as it's not rotating, taking derivatives works out exactly how you would hope it would work. Like, you look at this vector, you're like, I hope all I have to do is take the derivative of the x component, the y component, and the z component, and those are the components of the derivative. And that's how it works, okay? So for an example, for us, most of the time, the independent variable is going to be time, okay? So we're going to have functions that are like, let's say, the position vector is a function of time, and that's equal to t squared for the x component, 3t for the y component, and cosine of 2t for the z component. Okay? Then in that case, the velocity vector, remember, is the derivative of the position vector with respect to time. And we're going to use this notation a lot. Anytime you see a dot, that means a derivative with respect to time. It's just sort of a shorthand for that. So you can think of that as the same thing as this. Okay? So the velocity vector would be 2t for the x component, 3 for the y component, negative 2 sine of 2t for the z component. Any questions about that? Okay, so if the coordinate system isn't rotating, that works exactly like you would think and hope that it would work. Yes?
When you do higher orders, do you just add more dots?
Yep, that's right. That's right. So yeah, if you wanted the, so then the acceleration is the second derivative of p with respect to t. You can write that as p double dot, and that's equal to 2, 0, and negative 4 cosine of 2t. Okay, the second thing we need to talk about is the product rule with vectors. One thing, so before I get into it with vectors, remember the product rule for scalars, for, just functions that aren't vectors. So for scalars, let's do it like if you have a u times v, so say those are two functions of some variable, and you want to take the derivative of the whole thing. You do that as derivative of u times v plus u times the derivative of v. Okay. You could also do it like this. I mean, it's just a different way of writing it, but u prime times v plus v prime times u. There's nothing wrong with doing that, right? But in this class, don't think of it this way, because if you think of it the first way, so this is fine for scalars, but just don't think of it this way, because the one on the left is basically exactly what you do for vectors, and the one on the right will mess you up for vectors. Okay? All right, so for products with vectors, there are really three ways that you can multiply things to vectors. So there are three ways of multiplying things to vectors. First, there is multiplying a vector to a scalar. Okay, so let's say that we have, let's say that our scalar is u and our vector is v. Okay? And you want to take the derivative of those two multiplied together. You do this as the derivative of the scalar times the vector plus the scalar times the derivative of the vector. And so if you, usually we're going to be taking the derivative with respect to time. So if you think of this as, partly I'm just doing this to show you some notation that you're going to see. Okay, so what if you want to take the derivative of this whole thing? That's what that line means. We want the time derivative of that whole thing. It's going to be the time derivative of the scalar times the vector plus the scalar times the time derivative of the vector. Now that's if you multiply a scalar to a vector. What if you multiply two vectors to each other? Well, there's two ways to do that. There's a dot product between two vectors. So let's say that you have a vector u dotted with a vector v, and you want to take the derivative of the whole thing. It works out just the same as it did before. You take the derivative of the first vector, which gives you a vector back, and then you take the dot product of that with the other vector, and then you add that to the first vector dotted with the derivative of the second vector. And in this class, everything pretty much is going to be derivatives with respect to time, so you can write the time derivative like this. The time derivative of the whole thing is equal to u dot dotted with v plus u dotted with V dot. Okay. When I said up above, don't think this way. So far, both of these two would work fine thinking this other way, but the cross product is the one where this would mess you up. Okay, so the last one is the cross product. So let's say that you have a vector u crossed with a vector v, and you want the derivative. That is u derivative crossed with v plus u crossed with v derivative. But here's the thing you have to be careful of. I mean, if you think of it this way and not this way, you don't really have to think about it. It'll just always work out. But here's where it goes wrong. This is not equal to u derivative cross v plus v derivative cross u. Because in the cross product, the order affects the answer, okay? And the same thing with time derivatives. So if you have u cross v, and you want the time derivative of the whole thing, that's equal to u dot cross v plus u cross v dot. Yep.
So if you flip the cross products, it just does the inverse of the answer, correct? So u cross
Correct.
v is inverse of v cross u.
That's right. So this second term gives you the opposite of what you want.
Yeah. So not that I would do it, but if you did u cross or u dot cross v minus
Yes.
v dot cross u, that would work.
That would work. But don't anybody ever think of it that way. Okay. Yes, exactly. Okay, any questions about that? Okay, so now this actually gives us enough to see for the first time why do rotating coordinate systems cause problems? And the answer is when you take derivatives, any kind of derivatives, for us it's time derivatives, I guess, yeah, let's just think of the time derivatives. When you take time derivatives of vectors, that's when things go haywire. And I'm going to show you why, okay? So say that you have a vector, let's say you have this vector u. It doesn't have to be any, I mean, it's just any old vector. It's not a velocity or a position or anything necessarily, but it could be. And let's say that it's a function of time. Okay, and this vector, so, you know, I always write vectors just as a column matrix. But remember what a vector is a component in the x direction times some sort of physical thing pointing in the direction of x, right? And then a y component times some physical thing in the direction of y. And in physics, you've probably seen it like this. So I'm going to write it out. I don't really use this notation much, but I'm going to write it out like this. okay? Then if you take the time derivative of this vector, notice that these are, all three of these have a scalar multiplied to a vector, right? So this is going to be ux dot times I plus ux times I dot, the time derivative of that vector in the x direction. Are you with me on that? What is that thing? I mean, you've never seen anything like that before. And, okay, so yeah, you'd rather not have to deal with it. And then you have plus uy dot times a vector in the y direction plus uy times j dot, and then plus uz dot times the vector in the z direction plus uz times k dot. Okay? So these terms if these are non-zero, they're a pain to work with. You know, we're going to have to think of ways to work with those. But the good news is, if the coordinate system isn't rotating, what's the derivative of a vector that stays pointing in the same direction? You know, a unit vector that stays in the same direction, yeah?
0.
0, right. So, fortunately, I dot, j dot, and k dot are 0 if the coordinate system isn't rotating. And that means they're only there to cause trouble when you have a rotating coordinate system. They only cause trouble.
And the coordinate hat with a dot just means that coordinate with respect to time or over time.
Correct. Yep, exactly. And like when we get to talking about rotating coordinate systems, I'll give a little kind of intuitive sense of what that vector looks like and stuff. But for now, this is just kind of a first glance at it. But they only cause trouble when the coordinate system is rotating. Okay, so if the coordinate system is not rotating, look, we get back exactly what I said we got back for derivatives of vectors in non-rotating coordinate systems. The x component of the derivative is just the derivative of that number representing the x component. The y component is just uy dot. The z component is just uz dot. Okay, but things go haywire when I dot, j dot, and k dot are non-zero. Okay, all I want you to do is have that on your radar, and it's going to come up later. Okay. Any questions about product rule? And then the last one is chain rule for vectors. And this is really only going to come up in one way. So it's useful if you know the velocity vector of an object as a function of some position variable. I'm going to call it x, but it could be y or z too. So this is if you're given a velocity vector as a function of a position variable. Then the acceleration, okay, so remember that the acceleration is not the derivative of velocity. Don't think of acceleration as the derivative of velocity. That'll always mess you up. It's the time derivative of velocity. It's very important that you take the derivative with respect to the correct variable, okay? So the acceleration is dv dt, okay? But the chain rule says if you know v as a function of x, something other than t, then you can write the acceleration as the derivative of the velocity with respect to that variable, as long as then you multiply it by the derivative of that variable with respect to time, okay? So let me show you how you could use this. So for example, if you know that an object's velocity vector is equal to 5x negative x squared, okay, and you want to know what's its acceleration vector at x equals 2. Okay, well, don't think acceleration is the derivative of velocity. It's not, it's the time derivative of velocity, right? So acceleration is dv dt, but we don't know this in terms of t. So that's a problem. I mean, we can't take the derivative of this explicitly with respect to t, but what we can do is write this as dv dx times dx dt so that is 5 negative 2x, and now we have to multiply it by dx dt, but this is dx dt. Do you see that? This is Vx is equal to dx dt. Okay? And so multiplied by 5x, and so you get 25x negative 10x squared. Then evaluate that at x equals 2. And you get an acceleration that's equal to 50 negative 40. Okay, when we get to this kind of stuff, I'll bring it up again, but that's kind of the way we're going to use chain rule for vectors in this class. Anybody have any questions about that? Yeah.
So let's say it's velocity dependent on its position in the y
Yes.
direction, then our dy would be negative x squared.
Perfect. Yep, exactly. Exactly. Yep. Yes.
The coordinates for your acceleration are like representing a vector going from 50 on the x-axis to -40 on the y-axis?
That's right. So, you know, this object's moving through space. It's following some path, and this is saying when it's here, well, it wouldn't be there, I guess. Where would this maybe be plausible? Let's say over here, the acceleration vector is 50 in the x direction, -40 in the y direction. And so this is the acceleration vector at that instant.
I see.
Yep.
And then in three-dimensional space, you're just adding.
Exactly. Yep. Yep. It works exactly the same in 3D. All right. So that is the stuff that takes less time. And now we're going to get into the last topic, you know, so going through these topics one by one. We've done this one, this one, this one. So now we're going to get into solving ordinary differential equations using separation of variables. And ordinary differential equations, well, I'll write it out, but I'm going to abbreviate that ODEs. That's a common abbreviation. And we're just going to talk about one method of solving these, separation of variables. And if separation of variables could solve every ordinary differential equation, there wouldn't be 150 other methods. So this doesn't work for everything, but I'm going to try to be clear about what things it does work for, and this is the only thing you're going to have to use in this class. Okay, so ordinary differential equations, I'm going to abbreviate ODEs. The first thing is, what does it mean to solve a differential equation? Solving a differential equation means coming up with a function. You're not coming up with a number, you're coming up with a function. So you're trying to find the dependent variable as a function of the independent variable. And I'm going to put S in parentheses because you can have differential equations where you have more than one independent variable. So let me give an example. If you have a function, or if you have an equation, y double prime plus 10y prime plus y prime times y squared is equal to 50x, okay? Then what this is saying is, and maybe I could actually, let me make this more clear just with a different notation. So let's say that this is d squared y dx squared plus 10 times dy dx plus dy dx times y squared is equal to 50x. Okay? Well, since we're representing y, derivatives of y with respect to x, this tells us that y is the dependent variable. That's too many indents. Dependent variable. X is the independent variable because it's what we're taking derivatives with respect to. Okay, it just all, this is totally determined by what's in the top and what's in the bottom of those derivatives. And solving this differential equation means finding y as a function of x. Okay? An ordinary differential equation, hold on. An ordinary differential equation means there's only one independent variable. Okay, so like in our case, we're going to have ordinary differential equations because everything for us is going to have the one independent variable t. Okay, this is going to be t for us. So everything for us is going to be ordinary. The alternative to ordinary differential equations is partial differential equations. And that means that you have more than one independent variable. And because of that, it means the derivatives are partial derivatives. How many of you have seen partial derivatives in a math class? Half. So partial derivatives are like, for example, you know, it's the curly derivative looking things like df, dx, that kind of thing. So if you ever see those curly d's in the derivatives, those are partial derivatives. But we're not doing these in this class.
Is that what you need for like rotating coordinate systems?
Yeah, no, you don't need that for rotating coordinate systems. That's a good question. Because with rotating coordinate systems, you know, things are still just happening in time, and the only thing that's independent is time. And so,
I guess the reason I thought
Yeah.
that was because you you have multiple variables as opposed to just the one.
Mhm. Yeah, I can understand where you would think that, but we won't need that. We won't need to do this at all in this class. Partial differential equations will come up in heat transfer classes when you take them. If you keep going with mechanics of materials after like half of this class or more is in deform right after this. If you go on with more classes after deform, you'll start having partial differential equations, but not here. All right, well, I guess we'll stop there. I'm still just sort of setting this up, but next time, which I guess is Wednesday, remember we don't have school on Monday, I will talk about what kinds of differential equations you can solve by separation of variables, how to recognize it, and the good news is how to recognize it in this class is if I ask you to solve a differential equation, you can do it by that method. It's the only thing we're gonna do. Okay, so, all right, this afternoon, look for homework. I'll give you some little homework assignment. I'll see you Wednesday.